This video looks at unbiased prediction using steady-state estimates. The previous two videos concentrated on unbiased predictions using either a Karima model or a disturbance estimate, so that's two different methods. This video is going to give a third alternative, which is quite common when you have a state space model for the process. The key aim is to estimate the expected, and we should emphasize that, the expected steady state values for the state and input to give you a required steady state output. And then in effect you use deviation variables about the expected steady state. You can ensure consistency between predictions and the actual process if you ensure the estimated steady state is simultaneously consistent with both the process and the model. And this will be clearer as we progress. So a reminder of what happens with state space predictions. Assume first of all you have your standard model, yk equals cxk plus dk, xk plus 1 equals axk plus bu. Now if you assume you're at steady state whenever that happens, then you will have the following. You will have that yss, the steady state output, equals c xss, xss being the steady state plus disturbance, whatever that is, and also the steady state xss equals a xss plus b uss, where uss is the steady state input. If you take these two equations together, then what you find is you get a consistency equation, which is, I've just put this blue line around it. So yss minus d over 0 equals a matrix C0 A minus I B times a vector XSS USS. So we have consistency requirement between the steady state input, steady state output, and the disturbance. So the other thing you'll notice is a disturbance estimate is required before you can get steady state estimates for the state, the input, and the output. If you don't know D, then you can't progress with this particular method. Now, having got these consistency equations, you can basically invert the matrix and you find that the steady state and input depend upon the steady state output and disturbance, and you've got a very clean relationship there. Now, the other thing you might want to notice finally is the steady state output is usually a value that you can choose. It's likely to be something like the target. I want the steady state value to be 3 or 40 miles an hour or something like that. And therefore, on the left, you largely have known variables, and you can use these in order to infer what the required steady state and input will be. And you'll notice that they will vary as your estimate for the disturbance varies. Now, a state space model is linear, and thus you can use superposition. Why is that important? Well, here's our original state space model. Y equals cx plus d, x equals ax plus bu. And I'm now going to define some deviation variables, which are the distance from my desired steady state. You see I've got x hat equals x minus xss, u hat equals u minus uss, y hat equals y minus yss. I know that if I'm at steady state, the following equations must hold. Yss equals cxs plus dk, and xss equals a xss plus b uss. Now if I use superposition and these two together, along with the definitions of the deviation variables, then you can very quickly see that the following must hold. Y hat equals c x hat, and x hat k plus 1 equals a x hat k plus b u hat k. Why is that significant? Because you'll notice that this new model in the blue circle has no disturbance anymore. The disturbance has been absorbed in the definition of the deviation variables, and that's going to make my algebra somewhat simpler. Let's predict then with deviation variables. I already know that the steady state is defined by that, and what this implies that if I look at future deviations and the future deviations at the input are 0, then this is what I must get. if the future deviations of the input in 0, I would also expect the future deviations in the state to be 0, and I would expect my prediction equation basically to be around the origin. Now, I know that my state space model will therefore work. I know therefore that I must get unbiased predictions, because if I start from 0, which is what I'm doing there, I'm in the correct steady state, I'm starting from 0, I know that my future predictions will say you're going to stay at 0, and therefore using deviation variables will give me unbiased predictions, but it does assume that my estimates for XSS, USS and D are correct. Let's look at how we do the actual prediction then. Now, this was covered in the earlier videos, so I'm not going to spend time on it. You'll notice if you put in your state space equations and go through all the algebra, you will get a simple prediction equation based upon the deviation states and the deviations in the input. And that's just a reminder of how these deviation variables are defined. Basically the distances from the steady state. So I've not dwelled on that because it's covered in an earlier video. If we put this into compact form, again this was covered in an earlier video, the key thing to notice is that I've not done y hat future. What I've done is y future, and in order to go from y hat future to y future, what do I need to do? I need to add the steady state value. Okay? Because y hat future is the distance from the steady state. If I want the actual output, I need to add the steady state back on, and what do you notice over here on the right hand side? I've simply added the steady state output to every row. Okay, having done that, you find that the future predictions have this very simple form down here. Now, the definitions of px and hx and everything were covered in the earlier video. The key difference is that we're adding on this LYSS. So in summary, it's common to use discrete models for prediction, and this video has shown how you can form unbiased predictions using an equivalent to deviation variables. Now, here are the key steps. You need to estimate the steady state values of the disturbance states and inputs which ensure consistency between the model and the process. Once you've got those estimates, you can define your deviation variables, but the key thing here is it's reliant on these estimates here. These estimates have to be consistent. So your predictions will only be unbiased if the estimates for XSS, USS and YSS are consistent. Once you've done that, you do your predictions around the estimated steady state using nominal process parameters, and you don't need the disturbance term anymore. So you'll see my prediction is based upon just the deviation variable for X, the deviation variable for U, and I add on the steady state value for Y to get my predictions to the actual value that I need. And you'll see in summary here, just to remind you, because this is quite important, it's implicit that you have an observer which can be used to estimate both the states and critically a disturbance. You'll see the definitions of XSS, USS and YSS depend upon the value of the disturbance. Now, just an addendum for those who might want to look at it. What if the disturbance isn't an output disturbance, it's some other form of disturbance? So here, for example, I've said, what if you have an input disturbance? Well, your consistency equations are slightly different, and therefore the way you solve for XSS, USS and YSS is slightly different, but the principles are the same.